1.4b, continuous functions with limits, part 2. All right, what does it mean to be continuous? What is the definition of continuous? The limit
equals the function value.
As x approaches c of my function is equal to f of c. The limit is equal to the value. In layman's terms, we can draw it without lifting our pencil. All right? Because when we approach from both sides, we get arbitrarily close to a y value. That means a limit exists. However, when they touch, then it's said to be what? Continuous. Okay, when they touch, it's continuous. All right, that's what we're going to talk about again today. So for continuity at a point, again, the limit is equal to the value. However, we're going to talk about one-sided limits a little bit more. So if I have a segment and I go from A to B, can I do a limit as x approaches A? Can I actually do a limit as x approaches A? No, I can't. Because why? Okay, because it's an endpoint. However, if I do a limit as x approaches A from the right, can I do it? Yes. All right, so I can evaluate from the right. And then B, can I do a limit as x approaches B? No. Why not? There's an endpoint. However, can I go from the left? Yes. And so when we evaluate them, a limit is actually going from both sides, but we can talk about one-sided limits a little bit more on that. All right, so I have my function of square root 4 minus x squared. Does anybody know what kind of graph that makes?
Square root graph.
It's not actually a perfect square root graph. A parent function of a square root graph does that. All right. However, this one's a little bit different. Does anybody know what it is? This is actually a semicircle. And the reason why is a circle is x squared plus y squared is equal to r squared. We got to talk about those a little bit when we did polars. All right? Because if I actually solve for y, what would I do to actually solve for y? Subtract x squared, right? And so then I'd have like r squared minus x squared, right? And then I'd do what to it? I'd square root it. And technically it's a plus or minus. So it's in that form, which is a semicircle. All right? Now, Lane, you alluded to it perfectly. So what is my radius on this one? 2. All right? So it's centered at 0, 0, and my radius is 2. All right? Limit as x approaches negative 2. Before we would just substitute in, right? And I'd end up getting 0. Right? However, if I actually understand the graph of this, can I actually get a limit as x approaches negative 2? No, because can I actually go from the left? No, because if I do a little bit more than negative 2, like negative 3, all right, I'm just using, or negative 2.1 or something like that, what happens in my square root? It becomes a what? An imaginary, because it's 4 minus something bigger than 4. Is everybody following me? And so I actually can't go from the left anymore. All right, and so that's why I actually need this little superscript of a plus sign. So can I evaluate x approaches negative 2 from the right? Yes. And what is my limit as x approaches negative 2 from the right? 0. And so that actually goes to 0. So if I were to actually just do it orally, just to go to 2, which way do I have to approach 2 from?
The right side.
The left. I actually have to approach it from the left. All right. And so then my limit can exist. All right. Let's keep moving. This is called a greatest integer function. So when you have like 2 fancy brackets around a variable, that is called a greatest integer. Sometimes it's called a step function. I showed you the graph of what the greatest integer function looks like. And sometimes they refer to them as step function. That's the slang for it. But why do you think they do it? Because they look like what? Steps. All right, so I have the greatest integer of negative 2.6. So what's negative 2.6 in between? Negative 3 and negative 2. So what step is it still on? Negative 3. All right, the next one, I have the greatest integer of 5.1. So what's 5.1 in between? 5 and 6. So what step is it still on? 5. All right. Now, I'll do this one for Miss Walker. And so if I have the greatest integer of 6.7. All right. All right. If I have the greatest integer of 6.7, Miss Walker, what's it in between? 6, 7. So Which step is it still on? 6. The greatest integer is 6. All right. So if I want to do it the other way, though, let's say I have the greatest integer of negative 6.7. All right. So what is it in between?
7 and 6.
Negative 7 and negative 6. That'll be the next one. All right. And so what's the step still on? Negative 7. So now let's do it with a limit statement. And so now when we do this, we have a limit as x approaches 0 from the right of the greatest integer of x. All right. So what's a little bit from the right of 0? 0.001. Love that. All right. So if I have 0.001, if we kind of think of something from the right of 0, what's it in between? 0 and 1. What's it still on then? 0. And so this goes to 0. So when I approach the greatest integer of x as 0 from the right, it goes to 0. However, let's go from the left. So if I go from the left, though, what do I think of?
A little bit.
Like what? That's a lot. Like negative 0.001, right? And so it would actually still work out for me. And so what's it in between then? Negative 1 and 0. So what step is it still on, though? Negative 1. And so now if I have a limit as x approaches 0 of the greatest integer of x, what would that be?
Negative 1? Wait, mechanics. It doesn't exist. Wait, that one.
What is it? What is it?
It's oscillating, so.
What's a limit, guys, when you do what? You approach from both sides. When I approached from the right, it became what? 0. If I approached from the left, it became what? Negative 1. So if I take a limit as x approaches 0, what is it? It doesn't exist. Now tell me why. It's a jump discontinuity. That was good. That was good. All right. And so let's do another one. All right, Yamil, pick your favorite number.
4 and 1.
4. 4?
4.
4?
4.
Limit as x approaches 4. From the right or left?
Right.
Right. Love it. All right. So limit as x approaches 4 from the right of, let's say, the greatest integer of, what's your next one?
1.
1. 41. I like that. All right. And then we got x and then minus.
Say like 247. Alrighty, let's just do that real quick.
All right. Love it. All right. So I'm approaching 4 from the right of the greatest integer of x minus 247. I can tell you this is the first time I've done this example ever in my career. All right. And so if I go 4 from the right, is that a little bit more or less than 4?
A little bit more.
A little bit more than 4. Does everybody follow me on this? All right. And so if I do a little bit more than 4, dear goodness, this is a big negative. All right. So I have 4 minus 247. I got to think a little bit on this. What do I got? Negative what?
243.
243.
Yeah.
Now, that's a little bit what? More than 243. Is everybody following me?
Yeah.
Okay, because we went from the right. So what is, oh gosh. So what am I in between? I got to think of what number I'm at again. So what am I in between?
3 and 244.
Negative 243 and what? Negative 242. So what step am I still on? Negative 243. All right. More. All right. So let's do a limit as x approaches 3 from the left of greatest integer 2x plus 5. Yep, that's good. All right, cool. So 3 from the left, is it a little bit more than 3 or less than 3? Less than 3. So when I multiply 3 with the 2, is it a little bit more than, what's 3 times 2? 6. So is it a little more than 6 or less than 6?
A little less.
A little less than 6. So then I have a little less than 6 plus 5. So it's a little less than what? 11. So what is a little less than 11? What am I in between?
10 and 11.
10 and 11. So what am I at? 10. So that's how we deal with these greatest integers. Okay? Continuous functions.
A function is continuous in an interval if and only if it is continuous at every point in the interval.
Love it. Keep going.
A continuous function is one that is continuous at every point in its domain. Y is equal to 1 over x is a continuous in its domain negative infinity to 0 and 0 to infinity. So it is a continuous function. It is not continuous on negative
All right, beautiful. All right, so this 1 over x, this graph 1 over x, what does it look like? It's a very famous reciprocal function. It looks kind of like that. All right, where does this one break? We talked about when things break. Where does this one break? It breaks at 0, right? If we were to substitute in 0, we get a number over 0, which happens to be a what? A vertical asymptote, because we get a number over 0. So we got this reciprocal function. We have a vertical asymptote going on at 0. So that's where it breaks in our domain. However, this is a continuous function from negative infinity to 0 and 0 to infinity, because does 0 get included in my domain there? No, it's not. So this is actually a continuous function if I restrict it to those intervals. However, if I restrict it to negative 1 to 1, when does it break? 0. So I'm actually discontinuous on that interval because it breaks at what? 0. So let's put it into another terms. So if I have, let's say I have y equals, I don't know, 1 over x plus 2. All right? And I have the interval negative 3. No, I want to go further. All right. Negative 6 to negative 3. I like that. Negative 6 to negative 3. That's good. Is it continuous or not on the interval negative 6 to negative 3?
No, because there'd be a hole when x equals -2.
It's not a hole, but it's actually a vertical asymptote at negative 2. However, is negative 2 on my interval there?
Nope.
No. So on this interval, is it continuous or not?
Yes. Oh, yeah.
Yes, it's continuous. So it is continuous on this interval. All right? However, if I say, yo, dog, my interval is now negative 6 to 0. Now, is it continuous on that interval? No, it's not continuous on this interval. Why? Because it's vertically asymptotical at x equals negative 2. Exactly. All right? And so a lot of the times, if it's not on the interval that we care about, we're fine. All right? So if it's on the interval, that's all we care about. All right? And so that's kind of what I wanted to go with on that screen. All right, so let's look at this one. This is this is on your homework set. This is number 63. So we're going to find the constant a and the constant b, if we have a b, such that the function is continuous on the entire real line. What does it mean to be continuous again?
Basically, layman's terms, not lifting your pencil.
Okay, mathematically though, the limit is equal to the value, and a limit is going from what? Both sides. All right. So where's my problem area at on 63?
1.
It's at 1. All right. And so I need to take a limit as x approaches 1 from the left, and I need to take a limit as x approaches 1 from the right. So let's do left first. So which one am I substituting in 1 in for x? Just do it from the left. The top part of the piecewise or the bottom part of the piecewise? The bottom. And so when I do the bottom, I substitute it in and I get what?
Okay.
If I substitute in 1 right there, a minus 4. All right. So there's my limit as x approaches 1 from the left, a minus 4. Let's do it from the right now. So if I do a limit from the right, what do I get? I get 3 because I substituted in right there.
Oh, because 1 squared is...
So what do I want my limit to be? I want them to match up, don't I? I want it to be 3. So what do? I set them equal. So I have a minus 4 is equal to 3. So a is equal to 7. Now, for this, we are done. We are done for this problem. However, you need to be aware of if it actually is an equal to. The reason why is we want it to be equal to our value. So we want f of 1. And so what is f of 1? 3, because I substituted in this top part. Okay. However, on the AP exam, sometimes they'll try to trick you. In my BC class the other day, this didn't have an equal sign. It was just greater than 1 and like less than 1. And so did it actually have a value? No. So it was actually like a removable hole that they tried to trick some people on. And it worked. All right. This one, I have a piecewise function. I have 3 parts of this piecewise function. And the nice thing about these intervals is that I have x is less than negative 2, and then it's included in here. And so will I have a value on all of our problem areas? Yes. Okay, so that's a good thing to kind of notice. So everything should be good here. Where are my problem areas, though? -2 and at 3. And so we need to figure out both of them. So we're going to take 4 limit statements. So now we have a limit as x approaches -2 from the left. And we're going to do a limit as x approaches -2 from the right. All right. So when I go from -2 from the left, which one do I substitute it in? The top, bottom, middle? What are we doing? Top, definitely. All right. So when we substitute in -2 right here, so we end up getting what? 4, and then what?
Minus. No, plus. Is it going to be plus?
Plus 2k. There we go. So 4 plus 2k, and then plus 3. So we end up having 2k plus 7. All right, so that's my limit as x approaches -2 from the left. Now let's do it from the right. So when do I substitute it from the right?
The middle?
Middle one. The middle one. So what do we get when we substitute it in the middle one? -7. Love it. All right. And so now what do we do with those two things? We set them equal. So now we're going to have 2k plus 7 equals -7. So what do we get for k? -7. There it is. So k is equal to -7. All right. All right. Let's do it again. So where's my other problem area at? At 3. So now I do a limit as x approaches 3 from the left. And we're going to do a limit as x approaches 3 from the right. All right. When I go from 3 from the left, which one do I substitute it in? The middle one. So what do I get? 3. We get 3. So when I substitute 3 in from the right, which one do I substitute it in? The bottom. Is there anywhere for me to substitute it in at? No, because the bottom's always going to be what? 3 minus 2m. So now I have 3 minus 2m. So what do I want to do with them? I want to set them equal. So now I end up having 3 equals 3 minus 2m. Don't get confused on this one. So what does m equal? M equals 0. And so now that will have me have a function that is continuous when I have it that way. All right. So there we go. Numbers 17 through 24, 34 through 44, and 63, even though we did it. So really 64 through 66. Maybe 6, 7. All right.